Okay guys, good morning. This is day 2 of solving differential equations using separation of variables, and notice the topic that's going to enter today is the natural log of both sides. So a couple of quick warm-ups, rewrite another way. So when we multiply like bases, we add the exponents, right? Okay. So this will be an important concept that we will visit at some point during the lesson, and likewise this one too. Solve for the exact value of x. Now, last year, and as well as in Algebra 2, there was one of two ways that you learned how to do this. The first way would be to convert to log form. So literally, you would have log, and then you took the three parts of this exponential equation and you put them in the appropriate space for your logarithmic equation. So the e would go here, the exponent is what you're solving for, that would go over there, and this would be here. And log base e is ln. So we would have the ln of 4 equals 2x. It says solve for the exact value of x, so it's not like we're going to be putting this in the calculator or anything like this. We would just want to divide both sides by 2. So therefore the exact value of x is ln of 4 all over 2. Notice I'm not saying that it's ln of 2. I can't divide this 4 with this 2. ln of 4 is its own quantity, right? So this is your exact value. And this is actually how I do it in my Algebra 2 class this year. But then there was this other method that you more than likely were shown in pre-calculus last year, and that's to ln both sides, which is a strategy that we're going to use in our lesson today. So we would have the ln of e to the 2x equals ln of 4. You know, it's the same concept as if you were squaring both sides or multiplying by 5 on both sides. We're just natural logging both sides. And then we have the power property of logarithms that allows us to swing down this 2x. And ln of e, we encountered that a bunch of times this year. Ln of e is 1. So you really wind up getting 2x equals ln of 4, divide by 2, and you get the same answer that we achieved before. Just a slightly different way of looking at it. Okay. All right, so let's get to our first example of a differential equation where we might have to incorporate some of this past knowledge. Find a solution, y equals f of x to the differential equation. There we go. And here's our initial condition. Okay, so the first step, as we reviewed on Friday, is to separate the variables. And we cross multiply to start doing that. So we have e to the 2y dy equals 3x squared dx. And unlike Friday, our variables are already separated after we cross multiplied. So that works out really well in this example. So then we go to step number 2, which is to integrate both sides. Right. So we have to find the antiderivative of e to the 2y dy. And same thing on the right side. Right, so that's what we're looking at. Now, on Friday, both sides were power rule. We do not have that situation here. We do have a power rule that we're going to use on the right side, but this is an exponential function with a base of e. So we're going to have to review our sort of derivative formulas so that we can find our antiderivative, and we'll start talking about that over here, okay? Let's just get the right side done, since that's our power rule. So we're going to add 1 to this exponent, right? And then we're also going to divide the original coefficient by that new exponent as well. So that's really just going to turn out to be x cubed. We put the plus c on the right side, the side with the x variable. So if you don't mind, I'm just going to erase the 3 over 3 and just make it look a little nicer. And that makes sense because the derivative of x cubed is 3x squared, right? So we're sort of double checking ourselves, which is really how we're going to approach the antiderivative of e to the 2y as well, right? So on just a separate paper, we're just going to review a couple of derivatives of the exponential function with a base of e. So let's recall, if we had y equals, let's just say I wrote it too, that's not an e to the 2x plus 1, right? And I said differentiate, find the derivative. Well, the formula says that the first part of the derivative is the same as the original function times the ln of the base, which is e here, times the derivative of the exponent, which would just be 2, right? So the derivative is 2e to the 2x plus 1, right? ln of e just becomes 1. It's irrelevant here. So I want you to notice something, that the derivative and the antiderivative are very closely related, right? E to the 2x plus 1 shows up in our derivative as well as our original function, okay? And that's not a coincidence, that happens. But notice our antiderivative, did have a different coefficient than our original function, right? So let's see if we could put this together with a little trial and error. So if we're trying to figure out the antiderivative of e to the 2y, then the original function had e to the 2y as well, right? But if we do a little check, we will see that we are off by a little bit. And when I say check, meaning keep in mind that this is the original function, right? So let's just assume that we're correct. But we want to give it a little bit of a check. The derivative would be e to the 2y, right? So, I mean, looking good, right? But we would have ln of e times the derivative in terms of y here, which would be 2. So we are a little bit off if you think about it, because the derivative of what we're saying the original function looks like is not exactly what we want it to be, right? This derivative has to look like this. So we are off by a factor of something. So what you want to do is you want to say, well, my derivative really should have had a coefficient of 1 in the front. So you're going to ask yourself, well, what could you multiply this by so that you could achieve the correct coefficient? And if we did 2 times a 1/2, that would give us 1. And that 1/2 is important because that actually tells you what your derivative was off by. So now if I were to check, turn on a separate paper. Now if I were to check what we currently have as our antiderivative, The derivative in terms of y, well, coefficients we just dragged down. The derivative of e to the 2y is e to the 2y times ln of e times 2. And check it out, this 2 and this 1/2 would reduce to be just 1, which is exactly what we want. So now we are ready for step 3. So step 3 is to find the c value. And the original condition provided to us was f of 0 equals 1/2. Right? So this is our x, this is our y. Okay. All right, so we have 1/2 e to the 2y equals x cubed plus c. Okay, so 1/2 e to the 2, our y value is 1/2, equals, our x value is 0. And we are going to simplify this. And we're not going to be using a calculator. We're going to be leaving the c value in terms of e. So 0 cubed is 0. 2 times 1/2 is 1. So it looks like our c value is 1/2 e. Okay. Sorry about that. Get back in focus. Oh no. All right, there we go. Sorry about that, guys. All right, so step 4, we have to solve for y. So we have 1/2 e to the 2y equals x cubed plus our c value, which we now know is 1/2 e. All right. And again, we have to solve for y. Y is an exponent. We should start thinking logarithms eventually. We really have one more step to do before we introduce logarithms here. We do not want a coefficient other than a 1 here. So I'm going to multiply everything by 2. So that's going to give me e to the 2y equals 2x cubed. And 2 times 1/2 e is just e. All right, now we are ready to introduce logarithms. So going back to our method 1 and method 2 from our do now, I use method 2. I actually natural log both sides. It doesn't matter what method you use, method 1 or method 2. And the power property is going to allow us to bring down the 2y. Okay. Parentheses are very important. Over here we had a binomial and we're natural logging the entire binomial. So definitely make sure you have the parentheses around 2x cubed plus e. ln of e is 1, right? And then to get y by itself, all we have to do is divide both sides by 2. So y equals ln 2x cubed plus e in parentheses all over 2. Okay. Don't forget about step number 5. And you have to check the initial condition. So we're going to sub in 1/2 for our y And we're going to sub in 0 for our x. And we're going to see if this does simplify correctly. So what we see here is 0 cubed is 0 times 2 is still 0. And 0 plus e is e. And ln of e is in fact 1. Right? So it does check out. So it's not really until this moment that you should be circling this as your final answer.